Alright, so here we have a 2 kilogram ball initially moving eastward at a rate of 1.5 meters per second. It is acted upon by an F that varies with time, as shown in the force time graph below. Here's A, B, C, D, and E if you need to pause it, otherwise I'm going to get going. We're given an F of T graph. Here F is given in newtons, T is given in seconds, units checked out already, so you don't have to do any conversions. Let's go and do part A. Part A wants us to find the ball's momentum at 4 seconds. So the graph starts at 0 seconds, and then it goes to 4, and then from 4 it goes to 8. So here, in order to find the momentum at 4 seconds, I think the easiest way to do this one would simply be just to set up impulse. Impulse by definition is equal to change in momentum. I can break up delta P into PF minus PI, and here I can break up PI into MVI. I want to keep PF as is because it asked me to find the momentum at 4 seconds, indicating that it wants to find the momentum at 4 seconds. So you notice here on the right side of the function, I kept PF as my unknown. I didn't break it up into MVF. Why? Because I need to keep it as PF because that's what I'm asked to find. PI though, however, I broke it up into MVI. Why? Because mass is given, the initial velocity is also given. And then from here, really, the only thing I'm missing is the impulse, but I can find impulse by finding the area beneath an F of T graph. So here, I only shaded the first 4 seconds because the question here in part A asks us to find the momentum at 4 seconds. So I'm going to start at 0, go to 4. So if you do this particular area correctly, 1/2 times base times height. It's 1/2 times base times height because it's a right triangle. And here, the base is 4, from 0 to 4 is 4, and then all the way up to where the graph meets on the vertical axis, which is 10. So the height is 10. So it just be 1/2 times base, which is 4, times the height, which is 10, and that should give you an area of 20. Okay. Other than that, I'm just going to use that as my impulse. So the impulse, once again, is the area beneath an F of T graph. So because I found this area to be 20 and it's positive because it's above the T axis, so here I is equal to positive 20. And once again, PF is my unknown. I want to plug in M as 2, VI given as 1.5. It says eastward. So therefore VI is in the positive direction, so I'm just going to plug in a positive 1.5 here. I'm just going to simplify this. 2 times 1.5 is 3, but then this is negative 3. In order to solve for PF, I need to move the negative 3 to the left side of the equal sign, which makes it positive. So here on the right side, here on the left side, I have 20 plus 3, and simply the 3 comes from 2 times 1.5. Okay. All right. Other than that, PF is just simply 23 kilograms meters per second, or you can say 23 Newton times seconds. It doesn't really matter, but I do want to point out that I highlight the plus sign here because momentum is a vector, so it does have to have a direction. So therefore, the proper answer would be positive 23 kilograms times meters per second. All right, that's my answer for part A. Let's do part B. Part B wants us to find the kinetic energy at 4 seconds. Well, this is pretty light work. Here, I'm going to do 2 different strategies for you. The first strategy is just to kind of show you how to play with impulse and KE in terms of functions themselves. So here, you notice I just wrote out KE is 1/2 mv squared at 4 seconds here. But what I don't know is I don't know what V is, right? I know what M is. Okay, M is given as 2. But here, I'm just going to manipulate functions just to show you that there is a relationship between KE and momentum. So you notice on the right side here, I put P equals mv because by definition, momentum is the mass times the velocity. What I want to do though is I want to recognize that in KE, KE has an M and a V square, while momentum has an M and a V. I'm actually just going to square both of the left side and the right side. So squaring the left side equals P squared. If I square the right side, every term has to get squared, so it'd be M squared V squared. But here you notice I have a V square, which is essentially what I need in KE. Okay. So to get V squared by itself, I'm going to divide both sides by M squared. So this M squared here just gets moved to the bottom left. So I can say that V squared is P squared over M squared. Now, once again, I'm doing this because the KE term has a V squared. So essentially I can substitute it out. Okay. 1/2 gets carried down, the mass I haven't touched it. What I do know is that V squared can now be expressed as P squared over M squared. Well, here's an M on the outside of the parentheses, and then here's M squared, but the square will cancel out because M squared is implying that there's M times M. So therefore, 1 M on the top will cancel with 1 M on the bottom. So I can clean this up a little bit. I can say KE by relationship is just 1/2 times the momentum squared divided by M. Well, here's easy. 1/2 gets carried down. The momentum at 4 seconds, I already found that in part A. The momentum is simply positive 23 kilogram meters per second. So I can substitute it in for P, which is 23. and then the square term, and then m being 2, that's where this 2 comes from. So if I'm just going to square 23 and then divide it by 4, because 2 times 2 is 4 on the bottom, the square of 23 is 529. 529 divided by 4 will give you an answer of 132.25 joules. So that's our answer for part B. However, this is just, again, the first strategy to use it just to show you there is a relationship between KE and PE in case you're asked to derive any sort of functions in terms of KE or P. All right, now, most of you, hopefully, however, though, for part B, will go with this instinct. KE is 1/2 mv squared. You know what m is, m being 2. The only thing you don't know is v. But what you do know is momentum previously found in part A. The momentum at 4 seconds is 23. So you can just say momentum is equal to mv. The only thing you're missing is vf here. So therefore I can just substitute in, well, pf is 23 because I just found pf at 4 seconds in part A, which is 23. Mass is 2. Vf is my only unknown. So to solve for vf, I would just divide both sides by 2. So therefore vf here, which is equal to 11.5. Well, now I can just carry down this KE function, right? 1/2 mv squared, well, mass being 2. So the 1/2 and the 2 cancels out. What's my v at 4 seconds? Well, my v I just found is 11.5. Well, I'm going to square that. So the square of 11.5 will also give you the same answer of 132.25 joules. So as you can see, whatever strategy you use, as long as you're consistent, as long as your sciences are proper, the answer will work out. All right, let's do part C, D, and E. C is pretty light work. C asks for the impulse from 0 to 8 seconds. Once again, in case you haven't watched my other videos, here, when you're given force versus time graph, there's one essential information that you can pull out, and that is the area beneath an f of t graph is your change in momentum, which is your impulse, okay? Because part C asks the impulse from 0 to 8, I'm actually just going to shade in the other area that I haven't shaded yet, which is this right side. So once again, I made a statement here. Impulse is just the area. Which area? From 0 to 8. Why? Because they said so. All right, so in part C, I'm just going to go from 0 all the way to 8 seconds. I already found the first area, which is 20. Well, due to symmetry, the area on the right side in blue here, or aqua, whatever you want to call it, will also have to be 20. So therefore, the total area from 0 to 8 would just be 40, because this is positive 20. This is also positive 20 because both of these areas are above the t-axis. So therefore, my answer is just positive 40 kilograms times meters over second. Okay. All right. So that is the answer for part C. It's pretty light work. Part D wants us to find the change in velocity from 4 to 8 seconds. This one's a little longer. So to find the change in velocity, what you do have to recognize is that impulse is the change in momentum. Okay. So here I said I is equal to delta P. Now, what you do with the right side with this delta P is entirely up to you, but you just have to learn to be clever and how to break it up. Sometimes you break it up to PF minus PI. Here, I just broke it up actually to just M times delta V. Okay, so delta P is the same as M times delta V. Well, I say impulse is the change in momentum. So there's different ways to write really the same expression here. Now, why would I want to keep it as M delta V? Well, because part D asked me to find the change in velocity, which is delta V. So I don't need to break up delta V into VF minus VI. I'm actually going to keep it condensed as delta V because that's what I'm asked to find. So therefore, to find delta V, I need to get rid of this M here by dividing both sides by M. So to find delta V, I take the impulse divided by the mass. Well, what impulse? Impulse from 4 to 8. So if you look at the graph properly, the impulse from 4 to 8 is a positive 20, which is in blue here, right? So make sure you read your time boundary, okay? So for part D, it says from 4 to 8. I don't need to use 40 area. I actually just need to use 20 because this area that I found is 20. All right, other than that, the area here is positive 20. And then mass here is 2 kilogram. Units will cancel out. Kg will cancel out. So the only unit left over is meters per second. So my change in velocity here will actually be a positive 10 meters per second. Velocity is a vector, so that its change is also a vector quantity. It didn't use the word magnitude, so here I'm going to say that the object is speeding up to the right, so the change here is in the positive direction. All right, that is the answer for part D. So let's do part E. Part E asks us to find the change in kinetic energy from 4 to 8 seconds. Well, I'm just going to start with what it asked me. To find delta KE, I need KF minus KI. Here, I'm just going to break up KF into 1/2 mvf squared, and then KEI into 1/2 mvi squared. I notice here there's an extra parentheses there. I'm sorry, just ignore that. As a matter of fact, let me just go and delete it real quick. Okay. So you'll see the answer, but it's okay. I'll explain things to you. Okay. All right. So let me get back to where I was. All right. So here's 1/2 mvf squared minus 1/2 mvi squared. And then I know what vi is. Okay. The problem here starts at 4 seconds. I already found the time, the velocity at 4 seconds in my previous answer. And the velocity is 11.5. So if you need to pause the video, go backward, and see that I found the velocity at 4 seconds as 11.5 meters per second. So here, I know what m is, I know what vi is. The only thing that I highlighted in my work here is vf. I don't know what the velocity is at 8 seconds, but that's okay. I can find it really quick. Well, here in my statement, I know delta v is vf minus vi. Well, I can carry delta v from my previous part D, because part D is also from 4 to 8 seconds. Part E is also from 4 to 8 seconds. So I know that the change in velocity in part D is 10 meters per second. Well, change in velocity is just vf minus vi. Well, what's my vi? My vi is at 4 seconds. Once again, pay attention to your time bounds. Right? This particular part starts at 4 and it ends at 8. So therefore, my initial velocity here is 11.5 seconds as previously calculated. So I'm just going to plug values in. Well, what's my change in velocity? 10. VF is what I don't know. It's what I need to find. What's my VI? 11.5. So to get rid of, to get VF by itself, I need to get rid of the 11.5. It is a negative 11.5. So if I move the other side, it'll become positive. So 10 plus 11.5 will give me a value of 21.5. Now that I know what my velocity is at 8 seconds, I can just plug and chug. So I'm just going to carry my work down here. So delta KE is simply KEF minus KI. Be 1/2 times the mass being 2. What's my VF? I just found my VF at 8 seconds to be 21.5. I'm going to square that. Minus 1/2 times the mass, which is 2 once again. And then VI here being at 4 seconds, which is 11.5, right? So don't be plugging in VI being 1.5, right? VI is 1.5 at times equal to 0, but for part D and E, it starts at 4 seconds, so please do not make that rookie mistake and just plug in VI at 0. You want to plug VI at 4 seconds. All right, other than that, calculator time, 1/2 will cancel out, so really it'd be 21.5 squared minus 11.5 squared. So if you do this on your calculator, you'll get a difference of 330 joules, and that is your answer for part E, and that is this video. I hope that helps. Stay nerdy, don't be whack.